mismatch. I just said that like optical flow is the most traditional version of motion estimation, right? In optical flow, we want to find pixel correspondences between consecutive frames. But although I worked for a long time on optical flow, today I'm not going to talk about optical flow. I'm going to talk about long-term point tracking. What's the difference? The difference is in this long-term point tracking, we extend the correspondence problem into a long time horizon. Like we are not dealing with 2 frames now, we are dealing with like a number of frames, maybe hundreds of frames, right? How does it look like? Given a video clip, we are given also some query points to track. The goal is to predict trajectories, which are shown as colored lines here, over the whole video, over hundreds of frames, as I said. So these are the points belonging to the same physical surface in the world, okay? This is hard mainly because of 2 reasons. First, points appearance change across viewpoints, right? If we are tracking a point such a long time, then it's gonna look different at some point in time. And the second, it needs to work even though the point disappears for a while, right? We don't like it is occluded by some other thing in the world and then it reappears. We still need to be able to track it through these occlusions. And for occlusions, there is where the point is not visible on a certain frame, we also predict this binary visibility indicator, which are shown as black segments here in this colored tracks. I don't know if it is visible. So this is the problem that I want to talk about today, as I mentioned. But actually, ideally, if we had very ground truth optical flow, we could extend it to the long-term point tracking with just chaining, right? We have the flow from frame 1 to T, and then we have flow from 2 to 3. We could chain them up, right? We can achieve long-term point tracking by chaining this frame-by-frame estimations, ideally, right? What is the problem with that? When we do that, we have this problem of error accumulation due to occlusions, right? Let's say we have these 2 points that we track, like the red point and the gray point. And at some point, gray point occludes the red point, and then we start tracking the this IDC which occurs between the 2, and then we basically get penalized for this. So what I want to emphasize here is that in long-term motion estimation, we are focusing on tracking individual points across long horizons rather than relying on pairwise frame correspondences, because it won't work through these occlusions, which are unavoidable, right? I'm going to talk about mainly 2 works. The first one is most related to the theme of this workshop. It's a question actually that we wanted to answer in this workshop paper last year at ECCB. If we take any FOMO, visual FOMO, can it achieve long-term point tracking? And we tried many of them, like a bunch of them. I will show you in a second. Why did we think about this problem in the first place? Because vision foundation models or FOMOs in short, have shown this great generalization capabilities, right, across many tasks, such as Cutler in segmentation, CLIP in classification, DeepSec for localization, and many more, right? And we were interested in correspondence. Like correspondence is one of the fundamental problems in computer vision, and it is very important for many tasks like 3D reconstruction and so on. And there was actually some previous work exploring the capabilities of this visual foundation models for correspondence, but they were limited to this 2-view correspondence. There was no prior work assessing their abilities for this long-term correspondence problem in point tracking. Point tracking is different. It extends the correspondence estimation to longer temporal windows. We want to track the same physical point throughout this video frames, and we need to handle appearance changes, occlusions, and so on. It requires different capabilities than 2-view correspondence. That's what I'm trying to say here. And we took this foundation models and we checked their performance in point tracking as a way of evaluating their geometric awareness in these complex scenarios. We considered these 3 settings, mainly first zero shot. We used the one foundation model frozen directly. And in the ideal case, if a model can extract similar features of like a projected pixel of the same 3D point, then it's a great sign, right? And then what if we allow to modify it a little bit via probing, right? We can train these low capacity layers on top of the foundation model. And then we can also use adaptation techniques like LoRa to fine-tune the model, a technique which is widely used in LLMs to adapt them to the specific tasks. So that now, what kind of models did we consider? We considered a range of visual models trained with different objectives on diverse data sets. So first, models trained with self-supervision like mask autoencoders, MAEs, or Dino versions like Dino V2, and Dino V2 with registers. Then the ones that are trained with language supervision like CLIP, image generation models like Stable Diffusion, and finally models supervised for classification and segmentation like DIT or Segment Anything. For all these models, we just use the pre-trained checkpoints that are available. Okay, so let's start with the first setting, zero shot. This is, in the zero shot setting, we are not changing the model at all. So we are relying on the feature similarity for tracking. How did we do it? It's very simple. Given a frame, TQ, and a query point on it. TQ is for query frame. I will call it query frame, where the query is located, okay? And some other frame in the video. This can be any other frame, T, in the same video. We took these two frames and encode them with the foundation model and obtain the feature maps for each, right? Feature maps, capital F, for each frames. Then we extract the query feature Q using bilinear interpolation on the query frames features. And then we calculate the similarity of that query feature and the other frames features FT. What does this give us? This gives us a correlation map CT. Now, in the zero-shot setting, we don't do anything else. We simply find the most similar feature location to the query as our prediction. This is basically argmax, right? Like the predicted location P hat T is the index of the highest value in this correlation map CT. Now, this is very simple dot product between the query feature and the next frame's features. Now, and then argmax. Let's see how does it perform. We use tap-with benchmark. If you are not familiar, tap-with benchmark is a standard benchmark for point tracking. It consists of 3 data sets, tap-with, RGB stacking, and kinetics. We report here the delta, which is difference to the ground truth. You have your prediction, you have the ground truth location, you take the difference for visible points. And more accurately, it's the proportion of visible points that are accurately tracked within some threshold, like 1, 2, 4, 8, 16 pixels that are averaged. Okay, the higher better. And now here you see the performance of the foundation models in comparison to a supervised model, TAPNet. TAPNet is our like anchor point below, okay? So let's start with the Davis, leftmost column. On Davis, what we see is that Dino models performs the best. And then on RGB stacking in the middle column, we see that Stable Diffusion and SEM outperform Dino. Like I'm opening a parenthesis here. One reason we think could be due to the training set, because RGB stacking is a synthetic data set and Stable Diffusion has this diverse training set, including both real world and synthetic data. On average, in the last column, we see that Stable Diffusion achieves the best performance, followed by Dino V2. And on the right, you see the visualization of correlation maps for Dino V2 and Stable Diffusion. Like this is not confirmed experimentally, but based on our intuition, Stable Diffusion is more about location, while Dino is more about semantics, which could be like one justification why Dino performs better on Davis, more about semantic in this data set. Yeah, in summary, Stable Diffusion and Dino V2 perform the best in the zero-shot setting. Now probing. Now we will allow some training on top of the foundation model, right? Given the correlation map based on the outputs of a CNN, here in the reference TAPNet trains some lightweight convolutional layers to predict the locations and the occlusion maps. And we do the same for the foundation models here, basically. We first calculate the correlation maps on the output of a frozen foundation model, and then train some lightweight layers to project the correlation maps to outputs, right? This is like very lightweight layers on top of the foundation model, which is very similar to what is done by previous work. Now, for this experiment, we chose Dino V2. that require training. This requires training, right? And we need an efficient model. Stable diffusion was not very fast to train. Also, Dino is the second top performing model. What we see here when we compare probing to zero shot, probing results in better delta average than zero shot. It is also slightly better occlusion accuracy compared to TAPNet, the supervised model. So the conclusion here is probing improves over zero shot with closer performance to the supervised model. Lastly, we allowed update to the backbone, the Dino V2 backbone, using low rank adaptation. This is a way of adapting Dino to point tracking without having to fine tune it, right? LoRa allows us to do that, change the backbone for the task specifically. To be specific here, we applied LoRa to the projections of the query and the value in the attention layers of the VIT. So what we see here, adaptation improves the performance across all metrics, even outperforming TAPNet in the end in AJ and delta. So this is quite impressive, right? Adaptation can surpass the performance of the supervised model with fewer parameters to train. So for this part, I would like to summarize what I talked about. We compared visual foundation models for long-term point tracking. In the zero-shot setting, we found that Stable Diffusion and Dino V2 performed the best. Then we compared probing to adaptation and showed that adaptation can actually outperform the supervised model. And like one lesson maybe from this little workshop paper that we also used in the follow-up work is that these backbones, like Dino V2, can serve as a strong initialization for point tracking because they have this correspondence ability for long-term point tracking. One interesting future direction we wanted to explore for a while now is to use correlation maps across multiple frames. Okay, this concludes the first part. I'm going to move on to the second work, the TrackOn. TrackOn is a transformer-based online point tracking method with memory modules. We have simple transformer augmented with two types of memory. And this is again joint work with Görkay Veydi and Veydi's student. We presented it a couple of months ago at iClear 2025. Before I talk about TrackOn, I would like to tell you how actually point tracking methods work and what is common between them. Like why we emphasize this online thing. Why do we want to do it online? What does it mean to do point tracking online, okay? So if, I don't know if Adam is here, but so Particle Video Revisited, or PIPS in short, is one of the earliest deep learning methods for point tracking. It introduced these two ideas, which are still used to this day by point tracking methods. One is the dense cost volumes, these visual similarity maps, and the second is iterative optimization. What do I mean by that? This visual similarity maps correlates a query feature with the frame features. As a result, this gives us some similarity measurements at multiple scales. This is the idea behind the cost volume or similarity maps, and almost all methods use this because point tracking is about similarity. And the second idea is this iterative optimization. Why do we need iterative optimization? Because we are doing this tracking across frames, right? Again and again. And we want to update the position and the feature of the point while tracking it based on the new information that we have about the point on the new frame, right? And we do that by using all the information we have about the point so far, its position, feature, and cost volume related to, like part of the cost volume related to that point. We take all that information, give it to the update module, and this update module produces residual updates with respect to the previous location of the point. We take these residuals, update the point, and repeat this process k times. That's why we call it iterative optimization, because we compute these new correlation maps at the updated coordinates using updated features and so on. So it's exactly as it sounds. It's quite expensive to do these iterative updates. But this is basically the main paradigm with which almost all methods use in point tracking. This also leads to something that we think needs to be changed for real-time applications, the offline processing. What do I mean by offline processing? the methods process either the entire video or a large window of frames with this iterative updates, okay? Like you're allowed to look at all the frames in an offline manner. This, of course, allows high accuracy. We can see everything, all the information in all frames about the point by using both past information and future frames. But this is not applicable to real world scenarios, right? Like if you want to deploy this in a real world application like robotic arms or self-driving cars, you don't have access to future frames, right? We need to be able to track the points only with the information that we have so far, which is past and the current frame. You are not allowed to peek into the future. You don't have half of the window for offline methods, in other words. Another problem in processing this whole video is the scalability, right? Like if you are computing attention across all the frames in the video, this brings a significant memory head. And this is especially problematic for long videos or large frame windows. So we wanted to change this. We wanted to do online tracking. Hence the name TrackOn. TrackOn is short for online tracking. We do long-term point tracking in an online processing setting. Here, the model processes the video frames sequentially, one frame at a time or frame by frame, without having access to the future frames, right? We have a simple transformer-based model. We changed from regression to classification and refinement. I will talk about it more in a second. One thing that you are missing if you are doing online tracking is this temporal information, right? Like you don't have the future part, like half of the video is gone. Now you need some kind of additional thing to achieve temporal continuity. You need to update query representations, in other words. If you are not doing iterative updates, you need a way of incorporating temporal information. And we do that with memory modules. Like we take the transformer and augment it with memory, specific two types of memory, spatial memory and context memory. One thing we really cared about in this project is we wanted to keep it as simple as possible. We didn't want to complicate things. That's why like transformer, patch classification, refinement, done, right? Like the model is very simple. Another thing we really focused on is efficiency. Like if we really want to use this, if we want this point tracking to be available to real-time applications, we need it to run fast, right? Of course, real-time would be great, but like getting close to real-time, maybe even near real-time would be really nice. And that's what we achieved in the end. Okay, let me go into details a little bit. So we treat the points of interest as queries in the transformer decoder, right? Given the query point, we attend the current frame to update their features. And we train this model with patch classification based on similarity, followed by refinement through offset prediction with respect to the patch center. This is, if you are like, I guess we are all familiar with object detection models, right? They first, they refine the proposals locations. This is a bit similar to that. First, we classify patch location and then refine it to get pixel level accuracy within the patch. How does it look like? First, we encode the target frame, then treat interest points as queries of the transformer decoder attending to the features of that target frame. Then we calculate similarity using dot product. This is like cost volumes, the same idea. And then the highest activation gives us the rough patch location on this similarity map, right? One thing we realized is the correct patch is not always the most similar one, right? Selecting the most similar doesn't always work. For example, here the red patch is more closer to the ground truth, the green one, despite being the second most similar, where the most similar one, the blue one, is actually far away, right? And like you don't get the solution if you only look at the most similar patch. That is the idea. But the answer is there. Like if you look at top 5, you have it as the, for example, the second most similar one. And to address this, we decode the local regions around top K predictions. K is not very large. 3 in this case, but the largest we try something like 5. And then integrate information from these locations to our decoded query. And then when we calculate the correlation again, now this refined query is aware of the top K predictions. In other words, like via self-attention between these top K predictions, we allow them to talk to each other, re-rank, right? Like I will be most similar to the ground truth, no, not you, and this kind of thing. And we refine, re-rank the similarities. Now, starting with a rough estimation from this patch classification on the left, here the lighter colors indicate higher correlation. We refine the prediction using the offset head on the right. Here, you will see the importance of refinement if you look closely, because the blue dot here is the selected patch center, red dot is the final prediction, which is closer to diamond ground truth than the patch center, right? Now we are getting pixel level accuracy within the patch. Okay, this is basically the model, the transformer followed by classification and refinement. Now I want to talk about the temporal aspect, the memory modules. First, let me convince you that you actually need the temporal processing. You need a memory, right? What happens is that the target feature changes through time, right? And our model has no temporal information yet. You see tracks below, the start frame, middle frame, and the final frame, 3 frames, right? The car is turning and the points on it are, their appearance is changing, viewpoint is changing, right? And on the plot above, we see the decreasing similarity between the features of the initial query and the correspondences over time. The initial similarity indicated by the horizontal dashed lines. Initially, it's very similar, but through time, since the point's appearance changes, the similarity goes down, right? You're losing the point. This is drifting. To not lose the point, what do you need to do? You need to update its appearance, right? You need to change the initial query features with information that is available through time. To do that, we have 2 memory modules, as I said. First, we have the spatial memory. And our goal here is to overcome drift by storing some information around the model's previous predictions, right? We take predictions in previous frames like t-3, t-2, t-1, and decode the local region around the prediction using deformable attention, and then store them in the spatial memory. Spatial memory is just like a queue, like a FIFO, first in, first out, right? And then we update the initial query using the information from the spatial memory. Now, initial query can look at previous predictions, like how they look like in the past, and then use this information to update its appearance. Like we are incorporating temporal information from past predictions. Now, I will show you the same plot that I showed in the previous slide, the feature similarity plot, okay? But now, I want to convince you that that memory actually helps improving the similarity to ground truth. How do we do that? We have 2 things, right? We have the query feature updated with the memory, and we have the initial version of that, which is not updated with the memory. Now we compute the similarity of both to the ground truth and take the ratio, okay? If this is like as a way of quantifying the increase in the similarity after the update. If we have a similarity ratio score greater than 1 over the frames for different tracks, then it means that we are able to increase the similarity to the ground truth location on the target frame using the spatial memory. And that's exactly what we see here. For different tracks, the similarity goes up. The ratio is greater than 1 for most tracks here. So spatial memory actually helps keeping the information updated through time. But one thing that we noticed is that if we only look at the location, we are missing some other important information like context around the point, which is especially useful for occlusions. So we want information beyond position. We want to keep the history. This is like the full evolution by storing the decoded queries. So we call this one the context memory, and it provides a broader view of the track's history with like appearance changes, occlusion status through time, like it was visible, not visible for some time, by storing the points embeddings from past frame. We simply store the decoded queries and use them to decode the next frame, like previous decoded queries are used to decode the next frame. it is context, what we call as context memory is again a queue, which is a set of previous decoded queries. Okay, that's it. That's all I'm gonna say about the model. Now I want to show you the results, again on tap with Kubrick, which is a synthetic data set of 11,000 sequences. And we have the Davis, again, 30 real-world videos from the Davis video dataset. We have RGB stacking, synthetic dataset of 50 videos. This is about robotic manipulation. And then we have the kinetics, which is real-world, 1,000 real-world videos. This is a huge table. I want to walk you through it step by step. The next thing that I want to show you is the metrics. The delta is the proportion of visible points tracked within some threshold 1, 2, 4, 8, and 16 pixels. We have occlusion accuracy, accuracy of visibility prediction, average Jacquard, overall accuracy by combining the two. And all higher better, okay? Now, all the methods that we compare, one important separation that we applied here is offline and online settings. The gray highlighted ones are trained on a large number of real-world videos. So I guess it's not fair to compare others to those three. First, the results on Davis. Here, the bottom track-on is our method. What we see here, it outperforms all online and offline models, including the ones actually using real-world data in AJ and delta average. And among the top performing is one in occlusion accuracy. The next one is RGB stacking. RGB stacking is particularly interesting because it has these long videos with lengths up to 250 frames, and it is ideal for our model because one of our claims is scaling to long temporal windows, long temporal spans with the memory measures. And what we see here is that our models performs better than online and offline in delta and occlusion accuracy again. Despite the advantages of models working with videos, like they have additional access to these feature frames. Finally, kinetics. Kinetic is interesting because it has real videos, a variety of internet videos. And on kinetics, what we see actually is the importance of real world data. Like all these gray highlighted methods perform much better than the others. Despite this, ours actually perform comparably well, surpassing online and offline in delta and occlusion accuracy. Now, again, sorry for this large table, but I hope it gives the basic message, like online methods can actually perform close enough to the offline, like accuracy is not a concern here. So the memory modules, do they actually help? Here we have the spatial memory MS, context memory MC. I'm going to explain what IME in a second. It's inference time memory extension. And through these different combinations of using one memory or other or using them together, let's walk over the rows. The model A, this is without any memory, okay? And this performs quite poorly. This is like the worst version that we have. Without any memory modules, the performance goes down. So we need memory modules. The model B, we introduce spatial memory. Model C, we introduce context memory. Both improves the performance. Model C, especially in occlusion accuracy, because with context memory, we wanted to actually handle the occlusions. And in model D, we have both. This gives the best performance, showing that maybe they have like complementary strengths. And the last column is, so memory size is fixed at train time, right? We have this 24 frame windows and so on. But the number of video frames at inference might differ, right? We might get asked to track points across longer videos. We can actually extend the memory size during inference by linearly interpolating the temporal positional embeddings, which allows us to extend 12 to, for example, 48. And this gives, in the last row, you see that this inference time memory extension gives actually slight improvements by allowing adapting the tracking. Finally, here we show the importance of re-ranking or offset head. Here, re-ranking is quite helpful. Offset head is helpful with 1 pixel, delta 1 pixel accuracy, like this refinement thing that we mentioned. So one of the claims that I had in the beginning was efficiency, right? Here we show the frames per second with changing memory sizes on the x-axis. As you might expect, large memory sizes help with performance. The color shows the performance, by the way. The darker, the better. But it also decreases the frames per second, right? Like as you use larger memory, you will be slower. That's what this plot tells us. But nice thing is all of these versions provide some sort of flexibility, right? Depending on your application, whether you care about accuracy or frames per second, you can choose one of these models. This allows some kind of flexibility for the practitioners. Also, all of them use less than 1 GB memory, and we actually have a version which is the memory size 48, which can track points with like 17 frames per second. That's what I meant by near real time. Like 17 is not convincing. I think for real time, we need probably 25 at least, like even 30. But 17 might be a good compromise for some applications. So in this work, we proposed a simple but effective transformer-based model for online point tracking. And here we show that patch classification followed by refinement can be a good replacement for regression. And we introduced memory modules to enable this temporal continuity while processing long videos. We showed state-of-the-art results with this online model, closing gap to the offline models, and it has relatively fast inference. And as future work, in point tracking, main limitation is data, right? Especially real data. On the left, you see the training data sets that we use. These are synthetic Kubrick data sets. And on the right, you see the test videos, real world videos, right? There's this large domain gap between the two. Models are trained on synthetic. They struggle to generalize to real world. But in real world, how do you, like, you cannot ask someone to track points across hundreds of frames, right? This is quite painful to create data sets in real world. Most of the recent work uses real-world fine-tuning by using pseudo-labels, like they extract point tracks using existing methods. But this introduces some sort of bias because they inherit the failure modes of this teacher model. One promising thing is this stereo 4D datasets. Here we could reduce reliance on synthetic and improve generalization to real world by using these 3D reconstructions from datasets like stereo 4D. We could project these 3D trajectories to 2D by building large-scale real-world correspondence dataset and enable supervision for point tracking. Actually, there is more to explore at the intersection of point tracking and 3D using models like Monster or Duster, which provides 3D points, camera poses, and so on. And this could allow, this has a lot of benefits of handling occlusions, textureless regions, enforcing physical consistency, which is missing in the current point tracking methods. Thank you very much for listening. If you have any questions, I'm happy to answer.
Thank you for the great talk today. So we have a few minutes, so we can get pretty much questions from audience. Oh, yeah.
So it strikes me that first of all, thank you very much for the nice talk. Very interesting. It strikes me that point tracking is kind of a combination of the object segmentation, memory modules, and cost volume from optical flow. Do you think it might be useful in the future to combine the segmentation with the flow, like maybe taking inspiration from human visual systems and system?
Yeah, actually, the first work that I presented kind of proves that, right? Like when you cluster dino features, you see clearly objects. Like there are methods which does that, right? Like clustering for segmentation. And the point tracking benefits from this, I think. Like it is, as you said, a combination of semantics and geometry. And these models, like foundation models especially, already have this semantic understanding. So point tracking benefits from this. But explicitly enforcing points according to some semantic segmentation, etc., might not be needed since this information is already available in these models. But I'm not sure. This is an interesting future work. Okay.
Actually, I have one question.
sorry.
So it was pretty interesting to see there is the context module and context memory and treasure memory are complementary. But could you see some interesting qualitative results that each module, for which case each module helps?
That's very good. To be fair, after the publication, we realized you could merge them into one. So then I will be honest about it. Like you might not need actually two, but it's important what you store in this memory. If you only store position, it will not be enough. But if you store position, some appearance information, some occlusion status, then one memory is actually. Yeah.
Sorry for asking.
I should have mentioned this on the script that it came up. Okay. Thank you very much.